Today we continue our coverage in Chapter 3, and in particular we'll be discussing error probability calculations for both the map and the maximum likelihood. This is covered in Section 3.2 of the book. Also, the review of probability theory is covered in Appendix B, and of course there are also the course notes. I'll be making some explanation a little more fully than what is in the book. And in particular, we'll be looking at the two cases of on-off keying and antipodal modulation in order to give our first example of how to calculate the error probability. So we started our discussion last time with signal space analysis and how we were going to represent our time-varying signal waveforms in a vector space, and this vector space is called signal space. So the signal space analysis allows us to take our continuous time waveforms, both the signal which is transmitted, the noise which impedes it, and the received signal, and to transform it into a vector form in the representation as a vector in the signal space. So we take this received vector, once we have transformed the received time domain signal into a vector, and from this observation we have to make a decision on which symbol was transmitted. And we looked at the map receiver, which maximizes the a posteriori probability and which requires information on the a priori distribution of the symbols. And when that information is not available, we will turn rather to the maximum likelihood, or ML, receiver, which, as it says, maximizes the likelihood, which is independent of the distribution, the prior distribution of the symbols. So in order to make that decision, in order to maximize these probabilities, we have to analyze the noise, because in the end it is the distribution of the noise which determines these probabilities densities that we need to analyze in order to make a good decision. And once we know how to make a good decision, then we have to find how good a decision it is to quantify that, and that is where we're going in today's lecture. So the signal space, as you'll recall, we use a collection of basis vectors, that's these Greek letters C, and each one of the signals that we're interested in can be represented in the vector form by projecting the received time domain signal, for example here, onto these basis vectors. In the same way, the noise and the symbols can be represented. So if we wanted to look at the conditional distribution of the received signal, conditioned on which symbol was sent, we could write it as we do down here. So the probability of R of t, given that, let's say, symbol I was transmitted, is just the probability that the received signal is this symbol I plus the noise. And if we take this time domain representation and put it in the signal space, that the vector R is equal to the symbol I vector plus a noise vector which tilts it from its value. Now up here in the corner, I said that we sort of did this already when we were looking at the binary case, and now we're just going to try and make it a little more general. So for our noise analysis, we'll start with the noise vector, and each element of this noise vector is defined by the projection of the noise random process here on each one of the basis vectors. And so the projection, or the inner product, is defined as the correlation of these two signals over the time of a symbol. So the integral from 0 to t, n of t, times the basis vector cj of t, gives the jth element of this noise vector. So we know that n of t is a Gaussian random process. We assume that it's zero mean without any loss of generality. And because it is an additive white Gaussian noise, we know that the power spectral density of the noise is simply a constant for all frequencies, and we'll call that constant n0 over 2. If the power spectral density is a constant, that means that the autocorrelation function is a delta function. So Rn, here the noise process n of tau, is equal to n0 over tau times the Dirac delta function of tau. So what does that mean when we say that the autocorrelation function is this Dirac? Well, the autocorrelation function for a random process is by definition the expected value of n of t times n of t displaced by some lag tau. So what we know is that this expected value will be 0 for any delay which is not identically 0. Of course, if it's identically 0, it's the signal correlated with itself, which would not be 0. So because n of t is an additive white Gaussian noise random process, we know that if we take the integral is a linear operation, that the result, in this case a random variable because it's a single value, will be Gaussian as well. And in fact, it will be a Gaussian random variable in this case. So if we have a Gaussian random variable, we know that to find all of its statistics, we have to find its expected value and its variance. So we'll start with the calculation of the expected value. So the expected value of this element of the vector is the expected value of the inner product given here. We will assume for now that we can interchange the order of the expectation in integration. And when we make that interchange, now we have the expected value of the integrand, but the phi j of t is just a cj of t. It's just a basis vector. It's deterministic. It doesn't enter into the expected value. So we're essentially just taking the expected value of our random process. But we have assumed that this is 0 mean, and so that means that this coordinate in the vector must also be 0 mean. So it's Gaussian, 0 mean. The next point is, how do we calculate the variance? Well, the variance is just the expected value of the square of the component, given that it's 0 mean. So now we have to take the expected value of this product of two integrals. So our first thing we're going to do is write this product of two integrals as a single double integral. So we put in these products under one double integrand, and so we have n of t times n of z, phi j of t, and phi j of z. So once again, we're going to change the order of the integration and the expectation. And again, the basis vectors do not enter into the expectations since they are deterministic. So we have here the autocorrelation function of the random process. And we know that this is going to be 0 except when t is exactly equal to z. So this double integral will essentially become a single integral, because whenever t is not exactly equal to z, this expected value will be 0. When we have t equal to z, we get a delta function, and the integral of the delta function is just unity. So here we write it again. It's 0 to t, the double integral n0 over this delta function, t minus z. And this becomes, again, a single integral because the integral of a delta function is unity. So we have n0 over 2. And now we have this 0 to t of just the basis vector, and it's the basis vector squared. But you recall that we said we would choose basis vectors which are orthonormal, the normal meaning that they're normalized to have a unit energy. And so we know that this integral, no matter which basis vector it is, will give 1. Therefore, the variance of this coefficient in the noise vector will have variance n0 over 2, and that's true no matter what value of j, which element we're talking about. So we have found the mean and the variance for each one of the elements in this noise vector. Let me write this over here. So we have a noise vector, and this is all kinds of elements. And we know that if I take any one of these, that it will be Gaussian, 0 mean, and variance n0 over 2. So we have the probability density function for each one of these elements. But that's not enough to have the probability density function for the vector. If we want the PDF of the vector, what do we need to know? We need to know the correlation between elements of the vector. It's not enough to know just the density of each one of the vectors. So for the case of the Gaussian, that means that we have to look at the covariance. We have to find the expected value of the product of Ni and Nj. So by definition, this Ni and Nj are these inner products. The product of these inner products we can make into a single double integral, much like we did before. What's different here is that I is not equal to j, whereas in the previous example we had I and j together. But for the rest of the manipulation, everything is quite similar. We change the order of integration and expectations. We have the expectations here. The basis vectors are outside the expectation. Once again, we have a delta function, n0/2, t minus z. Once again, this drops to a single integral. So far, everything has been the same. What's different now is that we have the inner product of basis vector I with basis vector j. And again, now we're looking at, these are orthonormal basis. Now we're looking at the ortho part, that these are orthogonal from one another, which means that this inner product is 0 for every case except I equal to j. So basically, this is equal to 0 because we have by hypothesis that I is not equal to j. So we found that the covariance between any arbitrary two elements of this noise vector gives 0. Now, since we have Gaussian noise, when we say that the coefficients are not correlated, that means that they are independent. This isn't true for all random variables, but in the family of Gaussian random variables, having established that the variables are uncorrelated, that gives us the stronger result that they are also independent. So now, if I was going back to talk about these noise coefficients, I would say that not only are they identically distributed, by that I meant that no matter which index I used, they had the same density. I can also say that they are also independent. And so we often use the shorthand that these are IID, independent and identically distributed random variables. So to summarize, these are, again, each one of the elements is 0 mean, variance n0/2. They're independent, and therefore the density of the vector, which is just the joint density of the coefficients, in this case, that means that it's just the product of each one of the densities. So because of the independence, if I want to look at the joint density of the vector, it is just the product of the marginal densities of each one of the elements in that vector. Of course, this noise vector is of infinite dimensions, so I'll have the product over an infinite number of density functions. But the important thing is that we have gone from knowing the noise process is Gaussian, Adder-White Gaussian noise, and the basis set is orthonormal. And because of these two hypotheses, we are able to find the joint density function for the entire noise vector, and it's given by this form. And of course, each one of these densities is the same. It's a Gaussian density, so we can replace this with the Gaussian density written as 1/2 pi sigma, 1/2 pi sigma, exponential of minus, and now we're going to have each one of these nj squared, 2 sigma squared. So I have a product of exponentials, and what that means is that I can think of this. We can simplify it, but before we go on to simplifying it, let's just say again that what I needed in the beginning was to look at what is the probability density of the received vector given that I know which symbol is sent. So that is saying, what is the probability of the received vector being equal to the symbol vector I know that I sent, I assume that I've sent, plus this noise. And now I know the density of the noise. Since I know the density of the noise and I know the symbol, I now know this density because I know that what I'm doing is simply displacing the mean. Instead of being zero mean, it's now going to have this mean, which is this symbol that was sent. So that means that I can say that the density, the conditional density of R, given that symbol I is sent, is simply equal to this product. And now I've replaced each one of the noise sample as being the received signal minus the coefficient of the symbol in that direction. Okay, so now I'm conditioning on symbol I. So symbol I is the one I assume was sent. And symbol I has many coefficients, the j as each one of those coefficients. So why is it so important to have this conditional density? Because it is this conditional density that we exploit in finding our maximum likelihood and our map detectors. So if we want to maximize the likelihood is just this conditional density that I have found. So if I have a certain received vector I, R, so I have a received vector, a received signal R of t, which gives me the received vector R. If I want to decide which symbol was transmitted, what I do is for each one of these R's, I calculate what is that conditional probability. One after the other, I try it for each one of the symbols. And as I calculate it for each one of the symbols, I find which one is maximized, and for that one, I choose that symbol as being what is projected. Now we have taken care to make this the any number of symbols, not just binary, but it's very similar to what we saw earlier. And the same thing would apply to the a posteriori. The only difference with the a posteriori is that now we're going to weight this conditional probability based on the a priori probability of each one of the symbols. So again, putting it in cleaner mathematics, we would say that the map choice is the argument. Again, that means which value of this j actually succeeds in the optimization. Now we can write our previous results on what we know to be the density of the noise vector, and we see that we're going to have to maximize, and now we're going to deal with this fact that we have an infinite product. So although we have an infinite product, first of all, the maximization has nothing to do with this constant in front, so I can get rid of the constant in front, the same maximization here. And we can divide, and we can rewrite this product. Since we have a product of exponentials, we know that this is the equivalent of having the exponential where we now have a sum across the exponentials. So this difficult infinite product at least becomes a somewhat easier infinite sum, whereas now the sum is taken inside the exponents of the exponential. So continuing in that vein, we know that if we take the natural logarithm, that the natural logarithm is a monotonic function, so it will not change the sense of the maximization. Therefore, we will say this is the equivalent of finding the maximum, and now we just need this exponent. And because we had a product with the prior probabilities, it's the same as saying plus the logarithm of these probabilities. So it looks a little easier, this maximization that we're trying to look at now, because we're dealing with the sum and a set of weights that offset that sum. Once again, we can multiply by 2 sigma squared and move this, what was the denominator with our sum, over to the other constant. This just leaves our sum a little easier to deal with. And in fact, because of the negative sign, we can turn this maximization into a minimization. So finally, the map choice will be finding the j, the symbol j that minimizes this summation. So now we can look at this infinite summation and try to separate it into pieces. So imagine, let me go over here on the side, that I have this summation of k equaling 1 to infinity, and I break this up into a summation of k equaling 1 to n, plus a summation of k equaling n plus 1 to infinity. Now n here is the dimension of the signal space. What does that mean? The dimension of the symbol space, that means how many elements there are that are non-zero in the symbol vector. So the symbol vector, remember, is signal 1, here I call it JK, symbol J1, symbol J2, symbol JN, and then after that, they're all zeros. And this is by construction. That is because we chose, sorry, I'm falling off the screen here, sorry about that. That is because we chose our first set of basis vectors to cover the symbol space. After that, we extended the basis to cover the noise. So this is part of the symbol space, and this is the expansion to cover noise, but of course the symbols are not in that part. So all that means is that when I break this sum up into two parts, here the s's are, non-zero, but here all of the jk are zero by construction. That means that if I'm trying to find out how to minimize this sum, this part doesn't affect minimization. So we call that the theorem of irrelevance. So here's the theorem of irrelevance. Because the elements are all zero for k greater than n, then these this part of the sum from n to infinity does not change this minimization, and therefore they're irrelevant, and we can throw them out of the minimization. Which brings us to a very nice result here, that we have the sum k equal 1 to n of the difference between r and the elements of r and the elements of the jth symbol. And we can write that as the L2 norm of the difference between r and the jth symbol. So what's nice about this norm interpretation, this is a vector space, is it gives us a nice intuition, because what do we come with? We come back to choose the closest. Choose the closest. Only before, when we were looking at the binary examples, it was very simple to say choose the closest. We were looking at, one-dimensional space. Now we have this much greater result, which applies to any dimensional space. I could have a 50-dimensional space, and this 50-dimensional space, I still could think of it, interpret it geometrically, even though I can't imagine 50 dimensions maybe. This concept of choosing the closest applies no matter what the size of the signal space. And because of this, I struggle because I think sometimes you don't see what's different from all the development we did before and what we're doing now. And what we've done now in looking at this, what I call signal space analysis, is that we've taken what was very intuitive in the two-dimensional sense and now seeing that basically the mathematics is very, very similar, but it's of course much stronger now because it applies to really any arbitrary dimension for the signal space. So again, this is the norm and the finite basis of the signal space. So now we can write our map choice is to choose the signal that is closer to the received signal. So this is the definition of being close, is this to norm. Of course, we have a weighting which is based on the a priori probability. So I calculate the distance, and then depending on which symbol it is, I'll cheat a little and say, well, if it's like a really highly probable symbol, then it'll be like it's even closer. And if it's very unlikely, then it won't be quite as close. So this is the map choice. And closer to is this term. And the weighting is, of course, from the a priori probability. The maximum likelihood choice, well, we don't have to go through the math again. It's really just the same thing, except now we have no weighting. We just choose the closest symbol. So if we think of our signal space, we have a collection of basis vectors which defines our signal space. And now we say, well, we have a received signal. We project it into this space, and it becomes a vector which falls somewhere in this space. And now the symbols which could be transmitted are points in this space. And what I do is I look at the received signal in this signal space, and I say, well, whichever point it happens to lie closest to, that is the point which will be my choice, my maximum likelihood choice in detection. Again, this is directly related to the binary case that we looked at for one dimension. And closest was easy because it was just comparing the test statistic with a threshold. And that's basically the same concept that we have here, not infinite, in a arbitrary dimensional space. So the signal space analysis and this idea of assuming that we had a linear sampling receiver, and binary choice here, it basically gives us the same result. So here in the signal space analysis, I only represented it as a vector. I didn't say that it was a linear receiver and a sampling receiver. So this is a much stronger result because I've gone into it with a lot fewer assumptions. And again, signal space will make it easier to extend all of our intuition to the multidimensional case. So let's turn to an example from one of our previous exams. And so here are 3 signals defined in time over a 1 second symbol interval. One is constant, so a rectangle between 0 and 1. The other one is a cosine function. The other one is a cosine squared function. And the questions that we can ask about these 3 symbols is, first of all, are they equal energy? Well, these are questions to get you thinking and developing your intuition, your geometric intuition. So we know that we can represent these 3 signals in signal space by vectors. And we want to know, are these vectors all going to have the same length or not? So that's, are they equal energy? And what is the average energy per symbol? So you can guess they're probably not equal energy, and you can calculate what they are. And then finally, we would like to find the orthogonal basis for these 3 signals. And of course, we can use the Gram-Schmidt process, or in this case, I think you can be a little clever and maybe look at it directly. So I'll leave you with that example, and I encourage you to give it a shot yourself, and if you get stuck, to look at the solutions from the exam. Thank you.